must be in USTS1, but if you're using a regional endpoint, then that certificate must be in the same region as the API gateway stage. Finally, you must set up, of course, a CNAME or an alias record in Route 53 to point to your domain and API gateway. So that's it for this lecture. I hope you liked it, and I will see you in the next lecture. So let's open API Gateway, and we are in the API Gateway console. So as you can see in here, I have option of choosing an API type. So we have HTTP APIs, we have WebSocket API, REST API, which are public or private. And so as such, we will only deal with REST API for now. So we can try out the new console by clicking on this, and this is going to be the default very soon. So please make sure to have that, and then you choose REST API, and then you build it. So when you build an API, a REST API, you have several options. You can create a new API, you can import one from an open API definition file, so where it's a file and just import and the API is created for you. You can clone an existing API, or you can start from the example API. For us, we were going to start from a new API, and the name is going to be my first API. Now, as you see, for the API endpoint type, we have three options. We have regional, edge optimized, or private. So regional is going to be deployed in one region. Edge optimized is going to be deployed in many different regions, but it's at the edge that it's going to be deployed, and then the API will still live in one region. Or private is just private, not exposed to the web. To keep things simple right now, I'm going to choose regional API type. So let me create the API, and here we are. So now we're here, we're going to create our first method in this API. So for this, you click on create method here, and then we choose a method type. So it could be any of these HTTP verbs, but we're going to do a get, just to get a page. And then you have to choose the integration type. So as you can see, we have 5 options. We have Lambda function, HTTP, mock, AWS service, and VPC link. And the one we'll be testing is Lambda function. But I want to show you that we can also integrate with any service in any region. So we choose a region, and then we choose a service. And what it does is that you can expose some of your AWS services as an API through API Gateway. So we're going to keep things simple and use Lambda functions in this one. And so we need to choose a Lambda function, but for this, of course, we need to create it. So let's go in Lambda and create our function that is going to react to this API Gateway. So we create a function, and I call this one API Gateway root get. And this is perfect. And then the framework I'll use, the runtime is going to be Python 3.11, but whatever Python 3 or Python should work. So this is perfect. Let's go and create this function. And while this is creating, I want to show you the code we're going to use. So I am in my code in my folder, and there's lambda-code.py, and this is the entire code we're going to copy to Lambda. And so the idea is that this is a very simple Lambda function, which responds to an event with some context and says, hey, the body is going going to be hello from Lambda. It's going to be returned as the body. The status code is 200. And then the headers is content type application JSON to let our web browser know that we get back a JSON response. So I'm going to copy this entire code, scroll down, and paste it here. So we're going to deploy this function. So I'm going to click on deploy to deploy this function. And we can also test it. So for example, I can create a test event called demo tests. And then we just send this event, we save it, and then we click on test. And as you can see, the result is hello from Lambda with status code 200. So everything is working fine right now, and this is perfect. And what I'm going to do now is to integrate this Lambda function to my API gateway. So back in here, I'm going to copy the function ARN, go to my API gateway, and then just click and paste the ARN. Perfect. So now we have the Lambda function integrated. And because we want to see the full requests being passed to Lambda and being sent back from Lambda, you're going to tick Lambda proxy integration. Now for timeout, as you can see, even though a Lambda function can have a long timeout, for example, 5 minutes or 15 minutes, API Gateway has a limited timeout, and the default is 29 seconds. You can customize it and have it less than 29 seconds, but the default timeout is 29 seconds regardless of how long you
Hi everyone, welcome that you can do color overrides where you still and I'll just enable this. Install this and you can see certain changes in the appearance of my board. Now I'll install the community plugin style setting to customize my theme. I'll click on install and I'll just enable this. Here you can do all the customization that is available to do. The first one is colors. I'll be using the dark theme, so I'll just do the customization for dark theme. And here is the dark theme flavor. What flavor do you want? There are different options. I'll choose the one that feels good and I'm going to choose this mocha, and you can choose the dark theme accent. Here is the option to force custom flavor. What flavor do you want? There are different options and I'll just enable this. Here you can do all the customization that is available to do. The first one is colors. I'll be using the dark theme, so I'll just do the customization for dark theme. And here is the dark theme flavor. What flavor do you want? There are different options. I'll choose the one that feels good and I'm going to choose this mocha, and you can choose the dark theme accent. Here is the option to force custom accent. If you do not enable this option, whatever accent you have set in this appearance setting, accent color here, that will be applied across all of your board. So I will enable the option to force custom accent. There is also extended color schemes. I don't want that. You can do color overrides where you can change the color of the specified labels here. I don't want any of that, so I'll just close this one, and we have finished the color section. Now there is another option for file editor and markdown elements. The first option is for active line highlight. I will choose the highlight option, where if I
the function takes to execute. So let's create this method, and this is going to automatically grant API Gateway the right to invoke our Lambda function. So if I go back here and refresh this page, as you can see now, our API Gateway can invoke our Lambda function, and we can verify this by going into the configuration and then permissions. And if we have a look at the resource-based policy statement, this one, and we click on view policy, it turns out that my API Gateway is allowed to invoke my Lambda function if the source API is the one from my API Gateway, being root get. So this is the stuff that happens behind the scenes on AWS to allow the API Gateway to invoke our Lambda function. So we know that everything is done from a security perspective. So now we can have a look at our API Gateway. So the client for this one method sends a request, and we can have a look at the request itself here. So all the settings are here. It's done integration with Lambda, and so it's a Lambda type of integration with proxy enabled. Then the Lambda itself is this function. We can click on it and get back to our function. Then the response is proxy integration. That means that the API Gateway will parse what is being sent by the Lambda and interpret it. And then the method response is what we have here. We could modify it if we wanted to, but we're looking for application JSON. So let's test out this API. So for this, on the bottom right, there is a test, and you can specify some query strings or some headers, but we don't specify anything. Let's click on test. And the test is, hey, the response body is hello from Lambda. So as you can see from the API Gateway, The status is 200. That comes right from our code right here, which says status is 200. We also have the response body, hello from Lambda, again, was defined in our code right here. Body equals JSON.dumps and then hello from Lambda. And finally, the content type is JSON, and that is retrieved as part of the response headers being content type JSON. On top of it, from the test, we can have a look at the execution log from the API gateway, which is really nice, which is also when you want to debug and see what's happening, a very nice way of doing so. So we have done our first execution of an API gateway on top of a Lambda function. So now let's actually debug this and see what is being sent to our Lambda function. So I'm going to do print event, and then I'm going to deploy this. And we are going to invoke now our Lambda function again from our API gateway. So we're going to run a new test, which still says hello from Lambda, but this time we are printing the events. So if we go to the CloudWatch logs, we should be able to find it. So let's go into monitoring and then look at CloudWatch logs. We're going to find the latest log stream, this one. And here we have our log, and we can see here that this was the printed event that was received from API gateway. So some information you have in here, for example, the resource, which is slash, the path, slash, the method, which is get, and then you get headers, and then you get query string parameters and so on. So a lot of information is passed on by the API gateway to our Lambda function, and our Lambda function can use this information to forge a response and send it back to the API gateway. So now we can go ahead and actually create a new resource. So this time we're going to have the resource by doing this, and the resource name is going to be houses. So let's create this resource, and now we have the slash houses path that I just opened. And in slash houses, I'm going to create a method. It's going to be a get again for a Lambda function of proxy integration, and I need to create my Lambda function. So let's do this quickly. I'm going to copy this and then create a function, and it's not root get, it's houses get now. The runtime is still going to be Python, and let's create this function. Yet again, I'm going to just copy this code. And so instead of hello from Lambda, we're going to change the message to be hello from and then something with houses. So my function is now created. We're going to copy this, and it's going to be hello from my pretty house. Okay, we're going to deploy this. So now we have deployed the function. I'm going to copy the function ARN and paste it in here and create this method. And so now we have slash houses that has the get method. I can test this, so let's test it and click on test. And as you can see, I get a 200 hello from my pretty house. And so far it's pretty cool. We have the root get and we have the houses get, which invoke two different Lambda functions. But we want to be able to access this from a web browser, not just testing it from the API gateway UI. So let's click on deploy API, and we need to select a stage. So it's going to be a new stage, and the name is dev. We'll have a look at it later. Let's deploy this. And now that we've deployed this API, there's an invoke URL. So I'm going to copy this URL, and then I'm going to paste it in my web browser. And as you can see, when I go to /dev, it says hello from Lambda. So this is just Firefox doing a pretty print, but you get hello from Lambda. And if I go to /houses, then I get hello from my pretty house. So this API has two Lambda functions replying to me. And if I do something wrong, if I do /wrong, then I'm getting error message such as message missing authentication token. So here we go. We have deployed our API to API Gateway. And this is pretty cool because, well, we have two Lambda functions behind the scenes actually replying to it. And that's it for our basic tutorial on API Gateway. I hope you liked it, and I will see you in the next lecture. Now let's learn about the AWS step functions. So step functions is a way for you to build a serverless visual workflow to perform orchestration, and that's usually of your Lambda functions. So you would design a graph, and you would say at each step of the graph, in case of success or failure, what goes on next. And this is really cool because you can start really having some complex workflows within AWS. So step functions have some internal features such as sequencing, parallel functions, conditions, timeouts, error handling, and so much. And it doesn't just do Lambda functions, it does actually integrate with EC2 instances, ECS tasks, on-premises servers, the API gateway, the SQS queues, and DynamoDB, and actually a lot of AWS services. Also, it is possible for you within the step function workflow to implement a human approval feature. For example, a workflow goes up to some points and you say, okay, a human will have a look at the results. And if the human says yes, then please go on. If no, then fail. This is something that's possible thanks to the step functions. So the use cases of step functions are manifold, but like we can have, for example, the order fulfillment, we can have data processing, web applications, or any kind of workflow that is complex to describe and that would require some sort of graph for you to visualize it, okay? So that's it for this little intro. I hope you liked it, and I will see you in the next lecture. So now let's talk about Amazon Cognito. And the goal of it is to give user an identity to interact with our web and mobile application. So these users usually sit outside of our AWS account, hence the name Cognito, because it gives an identity to users that we don't know about yet. So we have two kinds of sub-services within Cognito. We have the Cognito user pool, and this provides a sign-in functionality for app users and has really good integration with API Gateway and the application load balancer. And we have the Cognito identity pool, used to be called federated identity, and this is to actually provide temporary AWS credentials to users that are registered with our application so that they can access some resources of AWS directly. And there is a good integration as well. see with Cognito user pools. So if you are asking yourself, don't we already have users in IAM? The answer is yes, you do. But Cognito is going to be for your web and mobile application users, which sit outside of AWS. So look for the keywords such as hundreds of users or mobile users or authentication with whatever mechanisms such as SAML and so on. So let's do a deep dive into Cognito User Pool, or CUP. So it's a serverless database of users for your web and mobile application. And you can define a simple login, such as username or email and a password as a combination. You have password reset feature. You can have email and phone number verification, multi-factor authentication for users, and you can also have integration with, for example, Facebook for your login or Google for your login, and so on. So this Cognito user pools, they integrate with the API gateway or the application load balancer. So if we take the example of the API gateway, the user is going to connect to your Cognito user pool, retrieve a token, pass this token to the API gateway, which is going to verify it. And then if it's good, it's going to translate it into the user identity, which will be passed to your Lambda function as a backend. And now your Lambda function knows the user it's dealing with and the fact that it has a very specific user that's been really well authenticated. Alternatively, you can also do the exact same thing with your Cognito user pool on top of your application load balancer. So that means that your application will connect again with your Cognito user pool, then pass it on to your application load balancer and make sure that it is a true login. And if it's true, it will redirect the request to your backend and pass in some additional headers with the identity of the user. So this really allows you to have in one place either your API gateway or your ALB, the certainty that you can verify the login of your user. So it's a responsibility that you've moved from your backend to the actual piece that is going to balance the load for your backend. So the API gateway or the ALB. Okay, the other sub part of Cognito is Cognito identity pools or federated identities. And it's to get identities for users, but this time they don't access our application through the API gateway or the application balancer, but instead they're going to directly access your AWS account using temporary AWS credentials. So the user's source can be, for example, users that are within Cognito user pools, or it can be third-party logins. The IAM policies applied to the credentials are defined within the Cognito identity pool service already, and they can be customized based on the user ID for fine-grained control. And in case you want, to have a defined a default IAM role, you can, so that your guest users or authenticated users that don't have specific role for you to understand what identity pools are. So let's say your web and mobile applications want to have direct access into an S3 bucket or a DynamoDB table. So we're going to have Cognito identity pools for this. So the web and mobile application is going to log in and get a token out of it. So it could be a login against Cognito user pools or a social identity provider or SAML or OpenID Connect and so on. And then it's going to take this token and pass it on to the Cognito identity pool service to exchange this token for temporary AWS credentials. And to do so, the Cognito identity pool is first going to evaluate whether or not the token passed is being correct, meaning the login is valid. And the second thing it's going to do is to craft this IAM policy that is specific to that user. So these credentials now will, thanks to this very temporary credentials with associated IAM policy, will be able to access AWS on your, for example, your S3 bucket or your DynamoDB table without going through an API gateway or an application load balancer. And this enables for you a use case where you can do row level security in DynamoDB. So you would, for example, have this policy coming out of the Cognito identity pools. And the idea is that in it, you have a condition, and this condition is saying that the leading key for DynamoDB must be equal to the Cognito identity DynamoDB table. That would be 2. Cognito is a very complicated service. Thankfully, you just need to know at a high level what it means. So it means that you can create a user base for your web and mobile application. It means you can enable row-level security in DynamoDB, for example, to get fine-grained access. And finally, remember remember this integration between Cognito, user pools, and your API gateway or your application load balancer. Okay, that's it. I hope you liked it, and I will see you in the next lecture. Okay, so let's discuss serverless architectures now, and we're going to create a mobile application called My To-Do List. So what we want to do is have the following requirements. We want to expose a REST API that has HTTPS endpoint. We want it to be serverless architecture, and we want the users to be able to directly interact with their own folder in S3 to manage their data if you want to. And users should be able to also authenticate through a managed serverless service. And finally, users can write and read to-dos, but they mostly read them, so maybe there's something to do around performance here. The database layer should scale and should have some really high read throughputs. So that's a pretty good requirement. Now let's see how we can do it. Number one is to get started, we have a mobile client, and we talked about doing a REST HTTPS thing, so let's use Amazon API Gateway for this. This is a great way of doing it. Now in the classic serverless API fashion, API Gateway will invoke a Lambda function, which basically allows us to scale and use serverless infrastructure. Okay, Amazon Lambda needs to be able to store and read to-do from a database that scales really well, that is serverless, is DynamoDB. So here we have DynamoDB as our backend. Now we said there was going to be also some kind of authentication layer going on. So for this, we can use a serverless technology such as Amazon Cognito. So our mobile client can connect and authenticate to Cognito, and then API Gateway along the way will verify the authentication with Cognito. And so that gives us a very classic serverless API that we've just created here. Nothing new for you here, but it's good to see it again. Now, if you want to give users access to Amazon S3 bucket, how do we do this? Well, we have our mobile clients that authenticates to Amazon Cognito, and Cognito that can generate temporary credentials for us and return these credentials to our mobile client. And these credentials allow our mobile client to store and retrieve files in Amazon S3 and basically access their own little space in S3. So this is a very classic question as well, how to do this. And the wrong answer is to store AWS user credentials on your mobile clients. You definitely do not want to do this. What you want to do is really use Amazon Cognito and then Amazon S3 with temporary credentials. Okay, so it's a very common question. So next, our app is starting to scale. We're starting to get more users, and it turns out that we, by looking at the patterns, figure out that we have a very high read throughput. So we have many RCUs, and the to-dos don't really change much. They don't get edited very often. So how can we change this architecture to basically improve the read throughput and decrease maybe the cost overall? What we can do is use DAX as a caching layer. So just before DynamoDB, we'll use DynamoDB DAX, and this will basically have a caching layer. And because we're doing so many reads, now the reads will be cached in DAX, and so DynamoDB won't need as much read capacity units. Maybe we'll scale better, maybe we'll have less cost overall because so many reads are cached. And this is a great way overall to keep on improving our architecture in a serverless fashion. Now there could be another way of doing caching. Maybe we want to use DAX, but maybe also we want to start caching the responses at the Amazon API Gateway level. This is also something we can do. And this is also a very good one if you think that the answers never really change and that you can start caching a few responses for a few API routes. So overall, really interesting to see these kind of architectures because they really show you how serverless is done, where the caching appears. And in this architecture, nothing is managed by us. We really pay per usage, and we really don't think about management of databases. All these things is done by AWS for us. So in this lecture, we've seen the classic serverless REST API architecture, basically leveraging HTTPS, API Gateway, Lambda, and DynamoDB. And then we've used Cognito to generate temporary credentials, which gives us access to an S3 bucket with a restricted policy. And we could use the exact same app pattern using Cognito, so our app can access maybe DynamoDB or Lambda directly or whatever. This is a very common pattern. Now, caching the reads on DynamoDB can be done using DAX. It's a very easy way to enable, and you can bring not only performance improvement but also cost reduction. And caching the REST request can be done at the API Gateway level if we have very static responses. Security, finally, for the entire thing, can be done with Cognito, and Cognito is directly integrated with the API gateway. So this was a very basic example, but it gives us started basically on serverless architectures and shows us all the different components we've seen in the past section. So I hope that helps, and I will see you in the next lecture. Okay, so let's talk about a serverless hosted website, maybe called myblog.com. So our website should scale globally. And we rarely write blogs, we often read blogs. So our blogs is seen by hundreds of thousands of people online, and we really add blogs, maybe one a day, one a week, but most of the time these blogs are being read. And so most of my website is going to be purely static files, and maybe a little bit of my website is going to be a dynamic REST API. I want to implement caching where possible to really save cost and save latency and have a great user experience. And any new users that subscribes to my website, to my blog, I really want them to receive a warm welcome email, and this should be serverless. And any photo uploaded to the blog, I also want to have a thumbnail being generated, also serverless, because I really like serverless. So how do we implement all these requirements? Number one, we want to serve content. It's static and it's global. So if you remember, we have our clients and our static content may be stored in Amazon S3. So how do we expose that bucket? Remember, the Amazon S3 bucket is in a specific region. How do we expose this globally? Well, we can use Amazon CloudFront, and Amazon CloudFront is a global distribution, CDN. And so basically our clients is going to interact with edge locations of Amazon CloudFront, and it's going to cache data coming straight from Amazon S3. Okay, super easy. We've seen CloudFront, we've seen S3, this is a classic architecture. Now, how do we do this securely? Now, that's a very common question as well. So we have the clients, it's interactive with CloudFront, and it's a global distribution still. But now we will add an origin access control, which will ensure that our Amazon S3 bucket can only be accessed by CloudFront. For this, we will add a bucket policy to only authorize the CloudFront distribution. Therefore, a user trying to access our Amazon S3 bucket directly will not be authorized, and we have secured our Amazon S3 buckets. Okay, so now we have this, and this is really good. How do we add a public serverless REST API? Well, for this, we'll have a REST HTTPS talking to Amazon API Gateway, invoking a Lambda function, maybe querying and reading from DynamoDB. And because we have so many reads, maybe DAX is a great caching layer we could use. Okay, so far, very easy. If we're going global, maybe we could be leveraging DynamoDB global databases to reduce the latencies in part of the world. That also could be a really good way of maybe speeding up our infrastructure and our architecture. Okay, so this is fine. We have everything we need. Now let's talk about the user welcome email flow. Well, here, remember, when a user subscribes, I want them to be having an email saying, hello, how are you? So for this, maybe in DynamoDB, we want to enable streams of changes. So we'll have a DynamoDB stream being created, and that DynamoDB stream will invoke a Lambda function. That Lambda function is going to be very special. It's going to have an IAM role, which allows us to use Amazon SES. So we haven't seen what Amazon SES is, but it's really simple. It's called Amazon Simple Email Service, so SES, and it basically allows us to send emails. So here, our Amazon Lambda function can use the AWS SDK to send emails from Amazon SES. And here we go, we have a basically serverless user welcome email flow, and really simple, no infrastructure to manage. It just works and scales really, really well. Okay, so now we said, okay, if users upload images, we want thumbnails to be created. So our client is going to maybe upload to our S3 bucket directly, or maybe again, we have an OAC and a CloudFront distribution, in which case our clients will upload photos to CloudFront, and CloudFront will forward them onto the Amazon S3 bucket, and this is called S3 transfer acceleration. So either directly to S3 or using transfer acceleration. And then what we'll do is that whenever a file is added to S3, it's going to trigger a Lambda function. So Lambda can be triggered by S3, and Lambda will be creating a thumbnail and putting that thumbnail into an S3 bucket. Could be a different bucket, for example. And just to show you that it's possible, Amazon S3 also has triggers to SQS and SNS. Now this is optional, and from SQS SNS you can do whatever you want, but it's just to show you that you're very free into how you want things to work. And so Amazon S3 can invoke either Lambda, SQS, or SNS, and you're really free to think about your solution architecture and how to make things serverless and easy for you on your end. So this is quite a complete architecture we've just done, but it's all serverless, it's all scaling globally, and I think that's what matters most. So we've seen static content being distributed using CloudFront with S3. We've seen the REST API that was serverless. We didn't need Cognito in this time because it was a public REST API, and we leveraged a global DynamoDB table to serve the data globally. We could have used also Aura Global Database, but in this case, it wouldn't have been such serverless. It would have been provisioned Aurora. We could also enable DynamoDB streams. Basically, these streams will tell us about changes to our user tables and then trigger a Lambda function. And that Lambda function had an IAM role attached to it, so it could use SES or Simple Email Service. And this was just to send emails in a serverless way. And S3, we've seen that it could trigger SQS, SNS, Lambda to notify of events. So quite a lot of learnings. All these things we know, but now it's, I think, really nice to see all these things working together and how we can create really cool applications using all the concepts we know. So I hope you liked it, and I will see you in the next lecture. Okay, so now we're talking about microservices. So not exactly serverless, but still a very interesting discussion to have. So we want to switch to a microservice architecture, and many services will interact with each other maybe using a REST API. So this is how they have interaction with each other. They just use the REST API. Each architecture for each microservice may vary in form and shape, so we're free to do whatever we want. And so we want to use a microservice architecture for the reason that we want to have linear development lifecycle for each service. We want each service to scale independently and have its own code repository. So this is why we would use a microservice architecture. Now let's have a look. So our users maybe will talk to our first microservice over HTTPS, and we've decided to have an elastic load balancer talking to ECS and then talking to DynamoDB. And it's just a choice we made. ECS, by the way, if you don't know what it is yet, it is for Docker, so for running Docker containers on AWS. So that's it. Now this microservice, usually it has a DNS name or URL, so maybe it's service1.example.com, and so to get all that information, maybe we'll do a DNS query to Route 53, get an alias record back, and then we can interact with that service. That's my first service, but maybe we have a second service, and this one is using a classic architecture for serverless, but instead of having DynamoDB, we'll have Elasticache. And again, just something just for fun, just to mix things up, but we can definitely use Elasticache as a backend for Lambda. So cool, everything works, but maybe that second microservice, service 2, maybe it also interacts with service 1. So the Lambda function will make a call to our elastic load balancer because it needs to get some information from the first microservice to be able to make a response. And then maybe we have a third microservice also using an ELB, but this one is not serverless. It's using Amazon EC2 autoscaling and an Amazon RDS database, so more of the classic architectures we've seen from before. And it turns out that maybe the EC2 instance must make a call to the second microservice before making a decision, so it's represented here by the dotted lines. And here the URL for this is going to be service3.example.com. So it's very simple, but what I want to show you is just have a quick discussion. You're free to design each microservice the way you want, and this is why I had so many different random architectures. There's two patterns for microservices. There is a synchronous pattern, so this is when we make explicit calls to other microservices. So API gateway, load balancer are a great way to do HTTPS calls to other microservices. But there is also an asynchronous pattern that I haven't been into a diagram, but using SQS or Kinesis or SNS or Lambda triggers for S3. All these things basically we're saying I'm going to put a message in SQS, but I don't care when I get a response. I actually don't care about the response. Something else will happen though, and this is an asynchronous pattern. So some challenges with microservices. The first one is that you need to have some overhead for creating each new microservice, and you may get issues optimizing server density or utilization. You may get complexity of running multiple versions of each microservice simultaneously. You may get a proliferation of client-side code requirements to integrate with many separate services. But so most of these challenges, or some of them, are solved by using serverless patterns. For example, API gateway, Lambda, they scale automatically and you pay per usage, so no need to worry about server utilization. You can easily clone APIs or reproduce environments in API gateway, and you can, for example, generate a client SDK through Swagger integration for the API gateway. So all in all, what I need to remember is that microservice is a design, and you can use AWS for that, and it does solve some problems and it does add some problems, but at least you get an idea of how things would work. Okay, that's it for this lecture. I will see you in the next lecture. Okay, yet another solution architecting we're going to see right here. So let's talk about software updates offloading. So we have an application, it's running on EC2, and it distributes software updates once in a while. So think of like computers that need to download a patch, and they need to download it from us, and this patch sits on EC2. So when a new software update is out, we're going to get a lot of requests because a lot of people want to update. And so the content is distributed in mass over the network, and it costs us so much money. Additionally, we really don't want to change or re-architect our application. We just want to optimize our cost in CPU. Is there an easy way for us to do it? Of course, the answer is yes, there is. So let's talk about the application current state. So we have a classic ELB plus ASG type of application running in multi-AZ, and we'll assume that these M5 instances are the instances distributing the software updates. Now, for simplicity's sake, let's say that these software updates, they're put into Amazon EFS, so all of them are in EFS. So how do we fix things? how do we basically enable this application to scale more globally and to reduce CPU utilization and to reduce cost? Super easy. We just put CloudFront on top of it. So CloudFront will be our savior. And why? Well, there's no changes to architecture. They will cache software updates files at the edge, because the software update files, they don't change. They're not dynamic. They're static. They're never changing. And so our EC2 instances, even though they're not serverless, CloudFront is, and it will scale for us. So that means that our ASG will not scale as much and will save tremendously in EC2 cost, network cost, EFS cost, and so much. And on top of it, we'll save on availability and so on. So remember, CloudFront is such an easy way to make an existing application more scalable and cheaper if it's mostly static content, just using some caching at the edges all around the world. So remember it. I find it pretty cool, and sometimes the best solutions are the easiest ones, and this is one example of them. So I hope you liked it, and I will see you in the next lecture. Hello and welcome to this section on databases. So I'm doing a quick intro because at the exam you will have to choose the right database for your workload, and there are a lot of managed databases on AWS to choose from. So it's mainly based on the architecture the question is asking. And so is it write heavy? Is it read heavy? Is it a balanced workload? What throughput does it need? Is it going to change or fluctuate during the day? How much data is going to be stored and for how long? Will it grow? What's the average object size? How often are they accessed and how are they accessed? What about data durability? What is the source of truth for your data? Do you have any latency requirements? Any concurrent user requirements? What is the data model? How are you going to query the data? Joins? Is it structure? Is it schema structure? Do you need a strong schema or do you need more flexibility? Do you want to include reporting on top of your database or not? Do you want search? Do you want a relational database or NoSQL? Are there any license costs? Do you want to switch to a cloud native database such as Aura and so on? So, of course, based on the question, you have a different answer, but this is to give you the kind of dimensions and the kind of avenues the questions can be geared towards for helping you choose the right database. But don't worry, we will see all the different databases in this section and summarize them. So first we have the RDBMS databases. That means you're using SQL or you want to do online transaction processing. So you have RDS and Aurora, and these databases are great if you want to do joins. Don't worry, by the way, we'll go into a deep dive in all these databases, so you don't have to remember everything. Then we have the category of the NoSQL databases. So NoSQL is going to be more flexible, usually, but you don't have join capabilities and you don't have the SQL query language in general, okay? There can be exceptions. And again, they will be discussed one by one. So we have DynamoDB, we have Elasticache, we have Neptune, DocumentDB, and Keyspaces, and there may be new names for you, but don't worry, we will learn about them in this section. Then we have object storage. So this is a kind of database. Yes, Amazon is free to store big objects, or Glacier to store backups and archives. Then we have data warehousing for SQL, doing analytics with SQL or business intelligence, BI. So we have Redshift, which is OLAP type of database, and Athena and EMR. We have the search type of databases. So we have the open search type of database to include some free text and do unstructured searches on your data. Graph databases, so to display relationships between your data sets. This is Amazon Neptune. We have ledger databases to have a list and a ledger of transactions. So we have the Amazon QLDB, so Quantum Ledger Database. We have the time series types of database for Amazon TimeStream, and that's it. We may have more database types and more databases that I will include in the section if need be, okay? So don't worry if some of these databases are not discussed in this section. They will be discussed at depth in the following section, which is the data and analytics section. Okay, so that's it for an overview. Don't worry, you don't have to remember anything from what I said. It's just to give you where we're coming from. And I will see you in the next lectures to start discussing the databases one by one. So let's do a summary of what we learned in the Amazon RDS section. And if you need to go back into any of these points, I suggest you go back to the old lectures. This is a summary to summarize what you should know out of Amazon RDS. So this is a managed PostgreSQL, MySQL or Oracle, SQL Server, DB2, MariaDB, or you have the custom version of RDS. In Amazon RDS, you need to provision an RDS instance size as well as an EBS volume type and size. So everything is provisioned, although you have auto-scaling capability for the storage layer. Amazon RDS supports read replicas to scale read capabilities. So if you have applications that need to run analytics against a production database, it is much better to create a read replica. And for high availability purposes, you can use the multi-AZ to have a standby database, although that database is just here for in case a disaster strikes, you cannot use it to perform queries against it. Security for your RDS database is done through IAM. So you can use, for example, username and password to connect to your database, but also you can use IAM authentication for some of them. You have security groups for network security on your Amazon RDS database, KMS for at-rest encryption, and you can have in-transit encryption using SSL and TLS. Now, if you wanted to do backups, you have the automated backup option, which is up to 35 days. And if you use that, you can do point-in-time restore to any point of time in these 35 days. and this will create a new database out of it. Or if you want to retain backups for longer term recovery, then you would use a manual database snapshot. There is a managed and scheduled maintenance, which will bring downtime into your database. So this is due to the fact that you have to provision it and that you have to update. AWS has to update at some point the database engine or the underlying EC2 instance for patches of security and so on. There is support for IAM authentication on RDS, and you can enforce it through the RDS proxy. And it has integration with Secrets Manager to manage the database credentials. If you wanted to have access to the underlying instance and customize it, then you can use the RDS custom option, and this is available for the Oracle and SQL Server type of databases. So the use cases of Amazon RDS is to store relational databases, for example, using the RDBMS, or have an online transaction. processing database, so OLTP. If you wanted to perform SQL queries on top of it, and transactions. Okay, so hopefully nothing is new for you here. Nothing is new for you here. I hope you liked it, and I will see you in the next lecture. So now let's do a summary of Amazon Aurora. So Aurora has a compatible API for two database engines, which are PostgreSQL and MySQL. And Aurora is a very special service because storage and compute are separate. So about storage, well, the data is stored in 6 replicas across 3 availability zones by default, and you cannot change this. Therefore, Aurora is highly available. On top of it, in case there is any issue with the storage, there's going to be a self-healing process behind the scenes happening. And if you wanted to increase the storage, no problem, there is auto-scaling out of the box. Now for the compute side, this is the actual database instances. They are clustered and they can be across multiple availability zones if you wanted to. And then if you had read replicas, you could auto-scale them as well to increase the load, to increase the capacity in case the load increases. Now, because you have a cluster of database instances, then you need custom endpoints to know where to write and read, and therefore you have a writer endpoint and a reader endpoint. You have the same security, monitoring, and maintenance features as RDS because end of the day they use kind of the same engine. And you need to know the backup and restore options for Aurora, which cannot summarize here, but I suggest you go back to that lecture if you ever need to. Now, some extra features you need to know about Aurora. The first one is Aurora Serverless. This is when you have unpredictable and intermittent workloads, but you don't need to do any capacity planning. So it is quite helpful in that use case. If you wanted to have a global database, you could use Aurora Global, and that gives you up to 16 database read instances in each region where your database is replicated. And the storage replication happens in less than 1 second, usually across regions, which is something you have to look out for at the exam. And in case you have a problem in your primary region, you can promote a secondary region to become your new primary. If you wanted to perform machine learning on top of Aurora, you could use the Aurora machine learning module to use SageMaker and Comprehend. If you wanted to use a testing database or a staging database out of your production database, for example, you could use the Aurora database cloning feature to create a new Aurora cluster out of the existing one, and it is much faster than doing a snapshot and restoring it. So the use cases for Aurora are the same as RDS, but you have less maintenance, more flexibility, more performance, and more features out of the box, which makes Aurora a great choice. Okay, that's it. I hope you liked it, and I will see you in the next lecture. So we've learned about Amazon Elasticache beforehand, so let's just do a quick summary. So Elasticache is a managed Redis or Memcached for Amazon, so it's a similar offering as RDS, but this time for caches technology. So what is a cache? Well, it's an in-memory data store, which gives you sub-millisecond latency when you want to read data. So for this, you must provision an Elasticache instance type for your cache, and then you're good to go. So if you are using Redis, you can have support for clustering, multi-AZ, and read replicas for sharding. And you have security provisioned through IAM. You can use security groups. You have KMS at rest encryption. And for Redis, you have Redis authentication. You have the same kind of features as RDS for backup, snapshots, and point-in-time restore. You have manage and schedule maintenance. And the most important thing that you need to remember for the exam is that if you decide to use Amazon Elasticache to perform some caching on top or combine with an RDS database, is that to use Elasticache, you need to modify your application code to leverage Elasticache. And so if the exam is asking you for a caching solution that does not require a code change, then Elasticache is not a good choice, okay? So the use cases for Elasticache are going to be key value store. When you do frequent read on top of your database, it's good to cache database queries. Also, if you have session data that needs to be stored for your users on your website, Elasticache is also a very good use case. And just so you know, you cannot use SQL on Elasticache. Okay, that's it for this lecture. I hope you liked it, and I will see you in the next lecture. So now let's do a summary of Amazon DynamoDB, which appears quite a bit at the exam. So DynamoDB is a proprietary technology from AWS. It's a managed serverless NoSQL database that provides you out of the box millisecond latency. You have two capacity modes you need to choose from. So one of them is the provision capacity with optional auto-scaling, which is great when you have a smooth type of workload that increases gradually over time or decreases gradually over time. Or you have the on-demand capacity mode, where you don't have to provision capacity, but it scales automatically for you, which is great if you have very unpredictable workloads or if you have sudden steep spikes of demand on your database. So DynamoDB can replace Elasticache as a key value store, and it's a great way to, for example, store session data for your website, combined with a TTL feature to expire a row after a specific amount of time. So DynamoDB is highly available. It is across multiple availability zones by default. The reads and the writes are fully decoupled, and it's possible for you to have transactions on top of DynamoDB tables. It is possible for you to create a read cache out of the box that is fully compatible with DynamoDB, which is a DAX cluster, DynamoDB accelerator. And the ability, the particularity of it is that you get then microsecond read latency. So look for that in the exam. In terms of security, authentication, and authorization, everything is done through IAM. You have event processing capability on top of DynamoDB. So you can enable DynamoDB streams to stream all the changes happening into your database. And you can have an integration to invoke Lambda from the DynamoDB stream. Therefore, Lambda can be invoked for every single change in your DynamoDB table. The other option is, instead of sending the data to DynamoDB streams, you can send the data to Kinesis data streams. The advantage is that on top of it, you can use the Kinesis data firehose feature, or you can use any type of integration that leverages Kinesis data stream. For example, you could have longer term retention up to 1 year on Kinesis data streams. You have a global table feature on top of DynamoDB, which allows you to do active-active replication across multiple regions. So anyone can read and write from any region. This is why it's called active-active. Now you have two backup options. The first one is an automated backup. You need to enable point-in-time recovery for that, and you can restore your table to a new DynamoDB table for any point of time up to 35 days. Or if you want to have longer term retention of backups, you can enable on-demand backups, which will also restore to a new table. Now you can export your DynamoDB table to Amazon S3 without using any of the read capacity units within in the point-in-time recovery window, so within 35 days, using the export to S3 feature. And you can also import from S3 without using any write capacity units into a new table. So DynamoDB, from an exam perspective, anytime you see that you need to rapidly evolve schemas, you need to have a flexible type of database schema, is going to be a great choice. So the use cases for DynamoDB is when you want a database and do serverless application development, and your data are small documents, for example, in the hundreds of kilobytes of size maximum, or when you want a distributed serverless cache. Okay, so that's it for DynamoDB. I hope you liked it, and I will see you in the next lecture. So now let's do a summary of Amazon S3 from a database perspective. So S3 is a key value store for objects, and it's great when you want to store big objects. It's not great to store many small objects. So Amazon S3 is serverless, you have infinite scaling, the maximum object size is 5 terabytes, and you can version objects over time. You have different storage tiers, so you have S3 Standard, Infrequent Access, Intelligent, and you have Glacier, and if you want to transition between the tiers, you can use lifecycle policies. Some important features you need to know about are versioning, encryption, replication, multi-factor authentication delete, MFA delete, and access logs. In terms of security, you have IAM security, but you can also have bucket policies on top of your S3 buckets. You have ACL, you have access points for Amazon S3, then you have S3 object lambdas to modify objects before they are sent to the applications. You have cores, and you have the concept of object lock or vault lock for Glacier, which you need to know about in depth. In terms of encryption mechanisms, we have different ones. We have SSE S3, SSE KMS, where you can bring your own KMS key. You have SSEC, you can do client-side encryption. You have encryption, TLS encryption in transit, and you can set a default encryption scheme for your S3 buckets. If you wanted to operate on all the files in Amazon S3 buckets at a time, you can use S3 batch to do batch operations. And this is very helpful, for example, when you want to encrypt unencrypted objects on an existing Amazon S3 bucket, or when you want to copy existing files from one bucket to another before enabling S3 replication. And to create this list of files, you can use S3 inventory, for example. In terms of performance improvements on Amazon S3, you can use multi-part upload to upload files in a parallel way. You can have S3 transfer acceleration to transfer S3 files faster from one region to another region, and S3 select to only retrieve the data you need out of Amazon S3. For automation, you can use S3 event notifications that has interfaces with SNS, SQS, Lambda, and EventBridge, and this allows you to, for example, react to events where new objects are created on your Amazon S3 buckets. So the use cases for Amazon S3 are around static files. It's going to be a key value store for huge files or website hosting. So hopefully I'm not teaching you anything new here, and if you have any doubts on any of these features, and they can all appear at the exam, then I would suggest you go back to the Amazon S3 section. Okay, that's it. I hope you liked it, and I will see you in the next lecture. Now let's talk about DocumentDB. So the same way we had Aurora as the way for AWS to implement a sort of big cloud native version of PostgreSQL and MySQL, we have DocumentDB, which is an Aurora version for MongoDB. So MongoDB, if you don't know, that's the logo on the top right corner of your screen. It is another NoSQL database, and you need to remember this for the exam. So DocumentDB is a NoSQL database, and it's based on top of the MongoDB technology. So it's compatible with MongoDB. So MongoDB is used to store, query, and index JSON data. And you have the same similar deployment concept as Aurora with DocumentDB. So that means it's a fully managed database. It's highly available. Data is replicated across 3 availability zones. And DocumentDB storage automatically will grow in increments of 10 gigabytes. And DocumentDB has been engineered so it can scale to workloads with millions of requests per second. So at the exam, if you see anything related to MongoDB, think DocumentDB. Or if you see anything related to NoSQL databases, think DocumentDB and also DynamoDB. That's it for this lecture. I hope you liked it, and I will see you in the next lecture. Now let's talk about Amazon Neptune. Neptune is a fully managed graph database. So an example of what a graph dataset would be, for example, something we all know, which is a social network. So if we look at a social network, people are friends, they like, they connect, they read, they comment, and so on. So users have friends, posts will have comments, comments have likes from users, users shares and like posts. And so all these things are interconnected. And so they create a graph. And so this is why Neptune is a great choice of database when it comes to graph datasets. So Neptune has replication across 3 AZ, up to 15 read replicas. It's used to build and run applications that are going to be with highly connected datasets, so like a social network. And because Neptune is optimized to run queries that are complex and hard on top of these graph datasets. You can store up to billions of relations on the database and query the graph with milliseconds latency. It's highly available with replication across multiple availability zones. And it's also great for storing knowledge graphs. For example, the Wikipedia database is a knowledge graph because all the Wikipedia articles are interconnected with each other. Fraud detection, recommendations engine, and social networking. So coming from an exam perspective, anytime you see anything related to graph databases, think no more than Neptune. Now, Amazon Neptune also has a feature called Neptune Streams. So streams in Amazon Neptune are going to be a real-time ordered sequence of data for every change that happens within your graph data in your Neptune database. So that means that whenever an application is writing to Amazon Neptune, then the changes will be available immediately after writing into that Neptune streams. So in that stream, you have no duplicates and a strict ordering of changes happening within your Neptune cluster. So in a graph, we have writes, and these writes are written, of course, to your Neptune cluster, but also to a Neptune stream. Now, this stream data is accessible using an HTTP REST API. That means that your applications, for example, that want to read your Neptune stream, can use this API to get all the changes in real time. So the use cases for enabling Neptune streams are, for example, to send notifications whenever some changes are made within your graph data, or to maintain your data synchronized into another data store. For example, you want to replicate the changes happening within your Neptune cluster into Amazon S3 or OpenSearch or Elasticache or more. Or if you want to replicate data across multiple regions for your Neptune cluster by looking at all the changes in the stream and rewriting those into a target Neptune cluster. Okay, so that's it for this lecture. I hope you liked it, and I will see you in the next lecture. So now let's talk about Amazon Key Spaces. And Key Spaces is a managed Apache Cassandra on AWS. So Cassandra is an open source NoSQL distributed database. And so with Key Spaces, you get Cassandra directly managed on the cloud by AWS. So it's going to be a serverless type of service. It's scalable, it's highly available, and fully managed by AWS. And it will automatically scale tables up and down based on the application's traffic. The table's data is going to be replicated 3 times across multiple AZ. And to perform your queries on top of Key Spaces, you're going to use the Cassandra Query Language, or CQL. So thanks to this, you're going to get single-digit millisecond latency at any scale, and you can do thousands of requests per second. 2 capacity modes to note. This is just like DynamoDB. You have the on-demand mode, and then you have the provision mode with auto-scaling, and these are the same things as DynamoDB, really. You get encryption features, backup, point-in-time recovery up to 35 days. And so the use cases is going to be to store IoT device information, time series data, and generally from an exam perspective, anytime you see Apache Cassandra, you just think about Amazon Key Spaces and you're done. Okay, that's it for this short lecture. I hope you liked it, and I will see you in the next lecture. Now let's talk about Amazon QLDB, which stands for Quantum Ledger database. So what is it? A ledger is a book recording financial transactions. And so QLDB is going to be just to have a ledger of financial transactions. It's a fully managed database, it's serverless, highly available, and has replication of data across 3 availability zones. And it's used to review history of all the changes made to your application data over time. That's why it's called a ledger. So it's an immutable system as well. That means that once you write something to the database, it cannot be removed or modified. And there's also a way to have a cryptographic signature to make sure that indeed nothing has been removed. So how does it work? Well, there is behind the scenes a journal. And so a journal has a sequence of modifications. And so anytime a modification is made, there is a cryptographic hash that is computed, which guarantees that nothing has been deleted or modified. And so this can be verified by anyone using the database. So this is extremely helpful for financial transactions because you want to make sure that obviously no financial transaction is disappearing from your database, which makes QLDB a great ledger database in the cloud. So you get 2 to 3 times better performance than common ledger blockchain frameworks. And also you can manipulate data using SQL. Now, as you'll see in the next lecture, there's also another database technology called Amazon Managed Blockchain. But the difference between QLDB and Managed Blockchain is that with QLDB, there is no concept of decentralization. That means that there's just a central database owned by Amazon that allows you to write this journal, okay? And this is in line with many financial regulation rules. So the difference between QLDB and Managed Blockchain is that QLDB has a central authority component and it's a ledger, whereas Managed Blockchain is going to have a decentralization component as well, okay? So that's it. Anytime you see financial transactions and ledger, think QLDB. I will see you in the next lecture. So now let's talk about Amazon TimeStream. And the name indicates that it's actually a time series database. So it's fully managed, it's fast, it's scalable, and it's serverless. So what is a time series? Well, it's a bunch of points that have a time included in them. So for example, here's a graph by year. So this is a time series. Now with TimeStream, you can automatically adjust the database up and down to scale capacity, and you can store and analyze trillions of events per day. The idea is that if you have a time series database, it's going to be much faster and much cheaper than using relational databases for time series data. Hence the specificity of having a time series database. You can do schedule queries, you can have records with multiple measures, and there is full SQL compatibility. The recent data will be kept in memory, and then the historical data is kept in a cost-optimized storage tier. As well as you have time series analytics function to help you analyze your data and find patterns in near real time. This database, just like every database on AWS, supports encryption in transit and at rest. So the use cases for TimeStream would be to have an IoT application, operational applications, real-time analytics, but everything related to a time series database. Now, in terms of architecture, TimeStream is here, and it can receive data from AWS IoT, so Internet of Things. Kinesis data streams through Lambda can receive data as well. Prometheus, Telegraph, there are integrations for that. Kinesis data streams as well through Kinesis data analytics for Apache Flink can receive data into Amazon TimeStream and Amazon MSK as well through the same process. And in terms of what can connect to TimeStream, well, we can build dashboards using Amazon QuickSight. We can do machine learning using Amazon SageMaker. We can do Grafana, or because there is a standard JDBC connection into your database, any application that is compatible with JDBC and SQL can leverage Amazon TimeStream. So that's it. I think from the exam, you just need to remember what TimeStream is at a high level, but I want to give you a bit more details as well. So that's it for this lecture. I hope you liked it, and I will see you in the next lecture.